Okay. Yeah. Right. This is now home territory. I'm talking a little about trilobites, not systematics so much as how they lived and how we, as scientists, can work out something about their life habits. Now, I've already said trilobites are extremely numerous, many species, and live in many different habitats, from shallow water to deep sea. One of the first questions that students always ask me is, why are there so many species of trilobites? It's a very easy question to ask, but a very difficult question to answer. So what I'm going to do today is to approach a few possible ways of attacking the question of why there are so many trilobites. Now, you all know what a typical trilobite is like, so I'm going to start with an atypical trilobite, and one that's important to me because it was the first one I ever named. This particular trilobite is very different from a normal trilobite because it has a very long, thin body, and the normal trilobite has quite wide pleurae. This one has little tiny ones here and here. Most of the body is an axis. It also has an enormous eye. There's the eye. That's the top view of the eye. That's the side view of the eye. And if we put the eye on the head, it sticks out beyond the rest of the head. It's a huge, great globular structure. And this was one of the first trilobites I discovered when I was doing my PhD thesis in the island of Spitsbergen in the Arctic. And a very nice one it was to discover. But it led me to wonder at the time, why this very peculiar morphology? Why was it so different from a normal trilobite? Then later I worked on another group of trilobites which also had enormous eyes. And I hope some of you can see from the front, this is the eye of this particular trilobite, here, all along the side of the head again, and they project from the side of the head like two convex lobes. Now, there are a number of ways you can approach life habits, and one of the ways is by comparing with living organisms which have the same adaptation. And if you look among marine arthropods, crustacea, you will find that there are a few species which also develop what we call hypertrophied eyes, extra large, huge eyes. Here's one of them, an amphipod called Hyperia. And this is the eye, which again occupies most of the head, just as it does in the trilobite. And this is one of those organisms, or crustaceans, which lives as a pelagic animal in the open ocean. Now, the majority of trilobites lived on the sea floor, but this particular kind of trilobite was likely to be a pelagic trilobite like Hyperia. And when you look at it again, you can see that this is quite a plausible explanation, because the eyes, the big eyes, which have thousands of lenses, I counted the lenses, there are over 4,000 lenses here, have lenses that face, this is looking upwards here, and sideways out at you, and even downwards, because some of the eye bulges out, so some of these lenses look downwards. So this was a trilobite that could look all the way around and up and down, 360-degree vision, which only makes sense if you are a swimming trilobite. Nearly all bottom-living trilobites, like this, look only to one side or to the other, not up and not down. So this trilobite, my first trilobite I named, is likely to be a pelagic animal. And this is a special lifestyle which interested me a good deal. This is a cyclopygid trilobite, a different family from the other, but some of the same adaptations, including enormous eyes with great numbers of lenses. So the second message is that this happened polyphyletically. More than one evolutionary origin developed pelagic habits. And in fact, I think it happened probably 3 or even 4 or more times. This is a summary of some of the trilobites that developed the same life habits, free-swimming oceanic life habits. One I particularly worked on is this animal called Carolinites, which occurs here also in China. That's the side view of 1 or 2 of these pelagic animals, in which you can see the great eye bulging out so that it can look even downwards and forwards. Now most trilobites also rest on the sediment surface with a flat bottom like this. But this trilobite has an eye hanging down below the rest of the animal, which only makes sense really if it is free swimming. This particular trilobite has spines that point right down to protect it from the underside. Many of these trilobites also develop forward vision, and in one case, or 1 or 2 cases, the eyes even become united at the front to produce a headlight, right? Literally at the front of the animal. So very exciting animals, particularly characteristic of the Ordovician period, which of course is the one I worked on. In my last lecture I mentioned these cyclopygids, this sort of thing, which appear very early in the Ordovician, that's one of the earliest, and carry on right through the Ordovician with very little change. Microperia Geology, for example, the same from the Irenic and from the Ashkin, very, very similar. This is a nice new drawing by my friend Keith Ingham, who does the best trilobite drawings I've ever seen, of this one particular species which several taxa get an eye united at the front. So it could see forward, it was probably swimming in a forward direction, in that direction. Now somebody will say, which way up did they swim? Did they swim like this, or did they swim on their backs? And that's a very difficult question to answer. I think probably they swam like that, but I can't prove it. And here's another of these strange animals with the united eyes at the front from one of Keith Ingham's drawings and specimens in the field. Now, one of the interesting things is we often know these from complete specimens because they lived out in oceanic environments. When they died or had to molt, they often came down to the seafloor. They had to do that to molt because all trilobites had to grow and get rid of their old coat. This to grow a new one. So we often have complete specimens of these, but sadly often flattened, not well preserved. Sometimes they are, occasionally they're well preserved. When did this habit start? Well, I've just written a paper very recently, 2007, on a Middle Cambrian trilobite, this one here, which evolved to look very similar to one from the Ordovician down here, which was also pelagic and the most specialized trilobite probably there ever was. This one lost its thoracic pleury altogether. It was described long ago by the great Czech paleontologist Joachim Baron. But so the first pelagic trilobites, I think, probably began as early as the Middle Cambrian, if we're right about this. They went all the way through the Cambrian, later Cambrian, through the Ordovician, up to the end of the Ordovician, where they died out in that extinction event I mentioned. At the end of the Ordovician mass extinction, goodbye pelagic trilobites. I don't think any subsequent trilobite learned to be pelagic. Correct me if you like, but can you think of any Silurian, Devonian trilobite with that morphology? No, I don't think so. So that's a very important lifestyle of the trilobites, and one that's quite easy to study. Now, this is a cyclopygid trilobite, and it's now swimming out towards you from the screen in this direction. So you can see it's seeing forward very well. And you can't see the lenses here, but there are thousands of very small lenses. There's another question to ask about these sorts of trilobites. Okay, they were pelagic. At what depth did they live? Because pelagic animals, of course, can be epipelagic, swimming in the surface waters, or mesopelagic, or even bathypelagic, living at great depth. You might think that's an impossible question to answer, but it's actually possible to answer a little bit, because I've already said this is a very old diagram indeed. It goes all the way back to my PhD thesis. I've already said that different trilobites inhabited different depths. So, platform faunas we talked about, the ones good for biogeography, and deep water faunas. Now, if you have a mesopelagic trilobite living at depth, it will have one feature of its distribution. It will only be found out here in what I call the biofacies, cyclopygid biofacies. It won't be swimming up here in the shallow waters. But if you have an epipelagic trilobite in the surface waters, of course you can find it all the way from here. It will swim out happily into the open ocean. Now these cyclopygids, the ones that look like this, we only find, in the early Ordovician at least, out here in this kind of habitat. So I thought, aha, these are going to be mesopelagic trilobites living at depth, not shallow water. But could one prove it? How could you go further and prove it? Just to show you in a much later diagram, here as an epipelagic trilobite living in surface waters, and this one, Carolinites, is very widespread around the world. The mesopelagic trilobites living at depth here, found only in offshore sediment. Well, now there's some terrible mathematics hidden away in there. It concerns something called the eye parameter, which you can actually measure from eyes alone. And the properties, the eye parameter of animals that live in dim light is different from the eye parameter of animals that live in bright light. In other words, if you have a mesopelagic trilobite, it should have a different eye parameter from an epipelagic trilobite. What you have to measure here are certain properties of the eye. The angle between each lens, the radius of curvature of the eye, the distance between one lens and the next, and so on. You feed it into this mathematical equation to get this value of the eye parameter. So, just using trilobite eyes, we can test this idea about epipelagic or mesopelagic life. The colours here show eye parameters for two different trilobites. One of them, let's go back just to remind you, one of them is this one, a mesopelagic one. One of them is the epipelagic one. We'll see most of that is green, and that is the supposed mesopelagic one. Most of that is yellow. That is the epipelagic one. We did this from a number of perfectly preserved trilobite eyes. And then, when you fit it on the curve based on the living organisms and their eye parameters, you find that the mesopelagic one is out here with night light and dim light insects, whereas the epipelagic one is here with diurnal, that's day-living marine crustaceans. In other words, the measurements from the eye parameter from the eyes of these trilobites is consistent with the idea of some being epipelagic, living in the surface waters, and some being mesopelagic, which I think is a very neat test of how a trilobite 450 million years ago lived in the ocean. We can also use it to test the ideas about distribution of these pelagic trilobites by paleogeography, which I hope now you know enough about to appreciate that if you have a pelagic trilobite, it's not going to obey the rules I've been talking about this morning. It won't mind if there is one continent and another continent, because it can swim across the ocean. Okay? So what you must compare it with is more like the graptolites in this case. These two diagrams show in the bottom the distribution of a living pelagic crustacean, an ostracod. You see, following the present-day paleoequator. Now, the epipelagic trilobite Carolinites, the one that lived in the surface waters, has the widest distribution, in my view, of any trilobite species. Back to your question, species now, really just one species that we know about. It goes, there may be some rivals for that, but it goes all the way around the paleoequator. That's Ordovician geography at the top. It's found in North America, it's found in Baltica, it's found in Siberia, it's found in Australia, and it's found in China, following the paleoequator. It didn't mind about ocean barriers, unlike nearly all trilobites, it swam across them. So that's a biogeographic test of the hypothesis about life habits. However, when you go to these rocks that contain these pelagic trilobites, mesopelagic trilobites in this case, the deeper water ones, you find some very different looking trilobites with them. This also has a big eye, but it's quite a different morphology. I can't go back to the beginning, nor will I, but just to show you, if you think of those early illustrations I've shown you, this animal has a much longer head. Still has very narrow pleury, bigger tail, and the tail has a dish on it. There's concave margin. And the head from the side has a big nose. Can you see that? Like a big, well, you know a shark. It's a bit like a shark's nose. And the eyes, although they're very big, are not bulging out. They are tucked in the side of the head here. There you can see it swimming out towards you. Looks a bit like a shark nose. Well, many years ago I showed this to a hydrodynamicist who said, well, this is a streamlined shape. Now this is a big animal compared with most pelagic trilobites. Most pelagic trilobites are this size. This animal can get up to this size. So what's going on here? The big-eyed trilobites are not well streamlined, but this one is designed to have a streamlined shape. In other words, it was an active, large, open ocean swimming trilobite. Can you test this hypothesis? Yes, you can. You can just look at it in a flume tank, and you can see how the currents go smoothly over the surface compared with many trilobites. Or you can do an experiment. You can suspend trilobite scaled model in a flume tank, with a flume tank, and measure the deflection of some strings supporting the animal in the current. If you have something which is well streamlined, it will not produce much deflection. If it is badly streamlined, it produces more deflection. Very simple mathematics, which is the kind I'm best at. That's the flume tank. And there's the trilobite model waiting to do an experiment. Here's the experiment. The trilobite is in there, in fact. So very careful, quite slow currents. You must have quite slow currents or you get turbulence problems. Trilobite is there. And we have a microscope over here to measure the deflection on the string supporting it. And I'm glad to say that the trilobite, well-streamlined trilobite, compared very well with any other trilobite for streamlining. So it was almost certainly a free-swimming, large trilobite in the oceans. What did it do? This is an unpublished diagram. It probably was a predator, chasing and feeding on smaller trilobites and very early crustaceans. There's nothing at that size. It's probably the only thing it could do. So we have now quite a complex picture of life in the open ocean of the Ordovician, with pelagic trilobites in the surface waters and at some depth, probably 400 meters, maybe even 200 to 400 meters, and big pelagic trilobites chasing them. Very briefly, I'm not going to talk about this because it's not the subject of my talk today. We also know, of course, about trilobites, how they grew from a larva, simple protaspis, to an adult. This is the first famous diagram, the first time this was worked out in detail, how a trilobite grew by releasing segments from the front of the tail into the thorax, which grows in number till it reaches an adult number of segments. So we can do trilobite ontogeny in considerable detail. We know about growth. Some of these larvae are extremely well preserved. That is a trilobite larva. It is about 1.5 millimeters long, a little bit bigger than one of your acritarchs, perhaps. But the preservation in this case is excellent. Now the point is that probably many trilobite larvae, but not all, were pelagic, swam in the open ocean and dispersed. But only a few trilobites stayed in the water column. Most trilobites, when they got larger, settled down and lived on the seafloor. But some trilobites stayed in the water column. It's quite an easy change to do. This, I might say, Shumadia is also very well known from China. And this is what happens in living arthropods. There's often a nauplius stage, which is dispersive, which settles to produce the adult morphology, say in a barnacle. Trilobites, well, most of them had protaspids, larvae, some of which were spherical and likely to be pelagic. When they settled, they really went through a metamorphosis and became quite different on the seafloor. Most noticeable of all, is probably nyliedes, nylieid larvae, which are huge, some of them protaspids, very big, and then they metamorphose completely when they settle. This is my attempt to put some limbs with Brian Chatterton back into a trilobite larva. They have a big, the underside is almost covered in some forms, except for 3 little holes, so I can imagine the limbs coming through these areas, helping it to swim through the water column. Another thing trilobites are famous for, of course, is the eye. Really the first very well preserved optical system in the fossil record. Most trilobite eyes are like the ones I described in the pelagic animals. They're composed of a large number of small lenses. Now this eye is a benthic trilobite, and you can see that it doesn't, very few of the lenses face upwards or indeed downwards. Most of them are facing sideways across the 7 We know how they saw because the C-axis, the optical axis of the calcite crystal, is normal to the surface of the lens. So only light coming from normal to the surface of the lens in this direction or this direction goes through into the eye. And there is a section through the lenses to show a normal type of trilobite prism, optical prism with the C-axis which emits the light coming down in this direction. Sometimes you get a puzzle, which I'm putting in because I hope somebody will have an answer for me one day. If you have the most efficient system for putting lenses together, it results in a series of hexagons, yes, 6-sided figures. But I have one trilobite, and maybe you know more, a pelagic trilobite in which the lenses are perfect squares. You can see here. I don't know if you've ever seen anything like this, no way, or do you? And I don't know why this is. I got quite excited because there is a kind of living crustacean which has square lenses, which lives also at depth in the ocean and has mirrors on the side of the lenses. But I tried this with a mathematical optician who says this sort of lens won't work with calcite. So it is not a reflecting lens. For me, it is a mystery. Just to show you, there are very interesting puzzles still to solve in the trilobites and their vision. Many trilobites, of course, have more specialized eyes, which are biconvex lenses, the so-called schizochrome eye, and they usually get fewer. They usually get fewer in number, much fewer. So many trilobites with those little lenses have thousands of lenses. These have hundreds or even tens of lenses, sometimes only 5 or 6. These are very sophisticated, specialized lenses. A lot is known about them. They have internal structures inside the lenses. They have barriers between lenses which cut out external light. And these lenses have been shown to have very precise focus, very specialized. They're called schizochrome eyes. But I recently described the most spectacular example of this that I know. That's the trilobite looking from above. This is from the Devonian of Morocco in Africa. Looks like an ordinary trilobite, doesn't it? But when you look from behind or the side, you'll see how special it is. Fantastic. Now we see this is a different lens, different eye from the pelagic eye completely. You can see how big the lenses are first. Second, you can see, this is looking at behind the trilobite. Second, you can see how straight the sides of the eyes are.